ID the Future, a podcast about evolution and intelligent design.
Hello and welcome to ID the Future. I'm Casey Luskin with Discovery Institute's Center for Science and Culture in Seattle, Washington. Today on the show, we have with us Guillermo Gonzalez. Guillermo is a research scientist at Telos One Scientific in Huntsville, Alabama. He earned a PhD in astronomy from the University of Washington in 1993 and has authored nearly 90 peer-reviewed scientific papers. He's also co-author of a major college-level astronomy textbook, and his work has led to the discovery of 2 new planets and has been featured in journals such as Science, Nature, and on the cover of Scientific American. In 2004, Guillermo Gonzalez co-authored the book The Privileged Planet: How Our Place in the Cosmos is Designed for Discovery, a book that is probably familiar to many ID the Future listeners. His latest writing is a book chapter in the volume Science and Faith and Dialogue, published by a South African academic publisher, AOSIS, and his chapter is titled Local Fine-Tuning and Habitable Zones. Guillermo is also a fellow with Discovery Institute, and it's great to have you on the show with us, Guillermo.
Thanks for having me.
Yes, well, we wanted to have a conversation with you about your chapter in this new volume, Science and Faith and Dialogue, which, by the way, is an open access book. We'll be sure to post a link to it in the description of this podcast, so folks who are interested in reading Guillermo's chapter can download it for free. But we want to talk about your chapter about local fine-tuning and habitable zones. And so I'd like to just ask you a start-off question here, Guillermo. When you talk about fine-tuning, what do you mean by fine-tuning? And you define this concept of global versus local fine-tuning. So what is the difference between global and local fine-tuning?
Okay, so fine-tuning very simply refers to the high sensitivity of the habitability or life friendliness of the universe to changes in the physical parameters. And I thought it would be a good idea to very explicitly separate the 2 kinds of fine-tuning that are sometimes confused or conflated together in popular discussion of fine-tuning, and that is local versus global. And so global fine-tuning refers to the universal or global properties of the observable universe, including the physical constants, the laws, and the cosmic initial condition. So examples of this would be in the fundamental particle masses, the strengths of the 4 fundamental forces, the cosmological constant, and the initial entropy of the universe. And so these are the kind of traditional things that physicists talk about as fine-tuning, the fine-tuning of the universe. And it's the fine-tuning of the universe for life. Now, I separate from these the so-called local fine-tuning cases. And so local fine-tuning refers to things that are not universal in their properties, things like planets, stars, and galaxies. So we observe these to be very different, observe a range of different kinds of stars, different kinds of galaxies, different kinds of planets. So we know these or cover a wide range of properties, and we know there are lots of them in the universe. So they're not universal, and that's why I call them local. They're local to the specific particular example or place in the universe. And so it's useful to divide it in this way, because then you can discuss how life depends on the local properties while keeping the global properties fixed. Or you can discuss how the small changes in the global properties, let's say masses of fundamental particles, propagate down to the local properties and become instantiated in the forms of planets, stars, and galaxies. Another reason it's useful to keep these separate is because observer selection bias, which is often discussed within the context of the anthropic principle, strongly affects the local parameter, but not the global ones, because we only know of one universe, one set of global physical parameters, but we know there are lots of stars and lots of galaxies and lots of planets, and they come over a range of parameters. And so you can consider those to be probabilistic resources. There's a lot of probabilistic resources for chance to have play. And so there is certainly observer self-selection bias taking place at the local level. Obviously, we can't live on a planet that's not compatible with our existence. You can't live on the surface of the moon. There's no oxygen, there's no water, etc. There are lots of places that are obviously ruled out, and therefore you can't have observers there observing that they're there because they're not there, because they don't exist. So that's the very simple kind of observer selection bias. And that really, it's very much a thing you have to keep in mind with the local parameters. And so that's, again, another reason to keep those separate.
So just to follow up on that, Guillermo, it sounds almost like some of these fine-tuning parameters, certainly the global ones, those have to be set at the origin of the universe. I mean, basically, those have to do with the cosmic macro architecture of the universe. Either it's there from the beginning or it's not there at all. And of course, those, as you said, some of those global parameters can influence local parameters and the ability of maybe local fine-tuning parameters that are life-friendly to develop. But some of those local parameters are not necessarily set at the beginning of the universe. They develop later, and they may depend on other factors that happen later on. Would you agree with that, or is that a fair way to?
That's absolutely correct. Yes, and so the global parameters are, you might say, set in stone at the beginning. That's what we're given, and astronomers, have looked for variations in some of the fundamental constants, by looking at very, very distant stars and galaxies, and so a large look back time, and they see that they really are constant. They don't vary from place to place in the universe. They are universal in that strict sense of the word. That's right.
Okay, well, let's dive into some of these local fine-tuning parameters, and I'm sure that there'll be global discussions as well. But you talk about the circumstellar habitable zone. What is the circumstellar habitable zone, or the CHZ, as you call it? And another question is Earth the only planet inside the CHZ of our solar system?
So traditionally the CHZ is defined as the range of distances that an Earth-like planet must have from its host star, so it can have liquid water on its surface from the heating it obtains from its host star. So modern boundaries or limits of the CHZ have been calculated to be about 0.95 AU. That's about 5% inside the current orbit of the Earth on the inner edge, out to about 1.35 or so AU for the outer edge. And yes, Earth is the only planet in the solar system within the CHZ. Venus is too close and Mars is too far. So it's like the Three Little Bears and the porridge, and Earth is just right. So that's a simple traditional definition of the CHZ, just depending on this requirement for liquid water, having a planet just like the Earth. You move it around, what happens to it, basically?
Now, I've heard that Mars had water, even liquid water, in the past. So even though it doesn't have liquid water in any appreciable amounts today, could it have been within the CHZ in the past, or could we have made that argument perhaps?
Yes, there's very strong evidence that Mars had liquid water on its surface early on, and for a couple of reasons, it lost that water either to space or to its crust, and none remains in liquid form at the surface. So yeah, you can say that Mars was within the circumstellar habitable zone for a relatively short time in the early history of the solar system. Now, the CHZ that I define as just a kind of an instantaneous value, an instantaneous CHZ. Now, Mars is also not like Earth. And so the definition of the CHZ depends on Earth-like planet. But Mars's habitation in the CHZ was very short-lived. And so the CHZ usually refers to a planet remaining there for some extended period of time. And so there's something called the continuously habitable zone, or the continuously habitable circumstellar zone. And Earth has remained within the circumstellar habitable zone over its history. And from geology, we know that liquid water has existed on its surface over essentially its entire history. And so the Earth has remained within the continuously habitable zone all that time, as the sun has been brightening even.
You could have porridge that stays at the right temperature to eat for a long time, or it might start off pretty cold, and pretty soon it gets so it's warm enough to eat for a few minutes, but then pretty soon it cools off and you don't want to eat it anymore. So
Right.
even the Goldilocks zone has its boundaries, I guess. So when we hear that a planet might have liquid water, is that enough to guarantee the existence of life, or at least that it might be habitable? And what else is needed besides just liquid water for a planet to be habitable?
So when we hear that a planet might have liquid water, certainly the first thing that pops into your head is that, hey, maybe there's life. And then certainly there is a very strong case that can be made that water is necessary for life, but that it's not sufficient. So it's one of the necessary requirements, but insufficient. Other things that you need for complex life, in particular on a planet, are 26 chemical elements out of the periodic table in the right proportions, widely distributed on the surface rather than being localized at one very particular location, and being recycled. so that, for example, when life dies, kind of sediments gets locked away in the crust, somehow it has to be made available again to the next generation of living things. So it has to be recycled. And so you need active geology to cycle these elements of life. For example, the carbonate silicate cycle is very important. It cycles the carbon back to the surface and it helps regulate the surface temperature. You need sufficiently low bolide impact rate, so sufficiently low impact rate of asteroids and comets over the history of the planet. You need a relatively quiet host star that's not too violently active, and probably have more to say about that later. You need a relatively stable surface temperature. For that, you need a relatively circular orbit, which the Earth has a very nearly circular orbit. Stable tilt of its rotation axis. No runaway buildup of greenhouse gases like methane or carbon dioxide. An atmosphere must have the right composition. And so if you're going to have complex life, you're going to have need to have a large oxygen concentration in the atmosphere, high nitrogen, and trace, but not zero, carbon dioxide, which you need for plants. And so these are some of the major things, other things you need for a planet to be habitable.
That's a lot of other parameters that are needed. And I mean, you mentioned sort of plate tectonics, and Mars doesn't have any plate tectonics. It's essentially, at least at this point, it's basically geologically dead. And Venus isn't geologically dead, but it doesn't have Earth-like plate tectonics. So
That's
there,
right.
you don't have plate tectonics to recycle those elements, which you need that for life. Let's consider another parameter that's probably, not thought about by a lot of folks. You talk about it in your chapter. I'm really glad you bring this out, but we kind of take it for granted. And that's planetary rotation, including the variation of its obliquity. Why is this important for planetary habitability?
So rotation can affect the distribution of the temperature on the surface around a planet. Right now, of course, the Earth's rotation period is 24 hours. And so, a given location on Earth is not in the darkness very too long, and 12 hours on average. But if it gets too slow to the point where, for example, that becomes synchronous with its orbit, meaning that one side of the planet always faces its host star, then you're going to have very large day-night temperature differences. In fact, any plants on the dark side, if the plants cannot exist on the dark side because there's no light for them. And there's a very real danger of the water freezing out on the dark side because it would act as a cold trap. So any water on the starlit side will eventually make its way to the cold dark side and freeze out. Also, the strength of the magnetic field that you generate depends on the circulation of the liquid iron outer core, and that depends on the rotation rate. And so you need a certain minimum rotation rate to maintain a relatively strong magnetic field, which helps protect the planet from particle radiation in space. Now, this one is a little bit more technical, but you have these two frequencies, you might say, or two periods that may interact with each other in what's called a resonance when these two frequencies are in sync. One of them is the core mantle spin, the spin of the core relative to the mantle, and the other one is a spin orbit. So the relation between the rotation period and the orbital period of a planet compared to the spin of its core relative to its mantle. And if these two come into resonance, you can dissipate an enormous amount of energy in the base of the mantle and generate a lot of heat all at once. And this is a leading theory for why Venus resurfaced itself, basically. About 700 million years ago, it went through one of these core mantle spin orbit resonances. And there's speculation that the Earth went through one of these resonances about 250 million years ago, creating one of the major mass extinctions. But it was more short-lived or not as energetic on the Earth because the Earth's particular spin. And so Venus is retrograde, and it's that retrograde spin plus the lack of a moon that led to it dissipating so much energy, whereas on the Earth, the tidal forces from the moon allowed the Earth to move away through this resonance very quickly. And so didn't spend much time on it. So that one's a more exotic, but an interesting case, but showing the complexity of some of these interactions that can involve the rotation of a planet, its geology, affecting the surface through the heat generation and so on. Now, the obliquity is a technical term for just the angle of the tilt of the Earth's rotation axis, or any planet. The Earth's rotation axis is tilted at about 23.5 degrees relative to its orbital plane. And this gives us mild seasons. So for one part of the year, the North Pole is tilted in the direction of the sun. The other half of the year, it's the South Pole that receives direct sunlight, and we get the mild seasons from that. The seasons will be much more severe if that angle, for example, closer to 90 degrees. Then you would, when you have one pole almost aimed at the sun, the other one aimed away, you would have one hemisphere of the Earth in darkness for a few months at a time, and then the other hemisphere, the opposite side of the orbit. So it would lead to enormous temperature swings. The other important thing about the obliquity is that it's stable. So not only is it at 23.5 degrees, but it stays there to within plus or minus 1.3 degrees or so. And so this also allows for very relatively stable temperatures. Even that's very tiny variation of 1.5 degrees or so on either side of 23.5 is detectable in the ice ages. That has a period of about 41,000 years, and we detect that as one of the Milankovitch cycles, that are so-called changes in very slight changes, subtle changes in the orbital characteristics of the Earth, eccentricity, precession, and the obliquity. And these have been manifested on the Earth's surface as the ice ages. And so even that small change is leading to some pretty dramatic changes, and it could have been much worse on the Earth.
So we also take for granted that a solar system will probably have rocky planets like Earth within the circumstellar habitable zone. You obviously have studied extrasolar planets and planets outside the solar system, and you're quite an expert and authority on this. So does our solar system, which has rocky planets inside of the circumstellar habitable zone, do we seem to be typical compared to other solar systems, or are we unique?
So this is really an interesting area of research. So much data has become available just in the last 20 years. There are now over 5,000 exoplanets known, detected with mostly space missions, such as Kepler and TESS. And it's other people have said this. It's not just me, that the solar system is beginning to look very weird, like the oddball system. So first of all, we have a relatively large number of planets, 8, and that's rare. I think the largest number of planets discovered to date, an exoplanet system, is 7, with TRAPPIST-1, and it might be a couple of those. But in these multiple planet systems, they tend to be extremely compact. So most of these multiple planet systems would actually fit inside the orbit of the Earth. Whereas, our solar system extends out to, the orbit of Neptune is the farthest planet. And so the solar system is much more spread out in terms of the sizes of the orbits of the planets. The orbital eccentricities or oblateness of the shapes of the orbits is very nearly circular, or have very low eccentricities on average for our solar system. Now, it's true that as the number of planets increases in these exoplanetary systems, the average eccentricity is seen to decline. So the exoplanetary systems with more planets have lower eccentricities, like our solar system, but our solar system still on average has a smaller eccentricity, even for its number of planets. Having a Jupiter in a large, nearly circular orbit is rare. So our Jupiter is relatively rare. The fact that we don't have a super Earth in our solar system is also rare. Super Earths are basically defined by mostly their mass. They're more massive than the Earth, and then up to about something like 5 Earth. That's the range that's called super Earths. And there's nothing like that in our solar system. Yet that's the most common type of exoplanet that's being found. Now, we also lack Neptune-like planets in tight orbits. So again, Neptune-like planets are also very Neptune mass and probably like in that they have very thick atmospheres. Are also very common, almost as common as the super Earths. And again, they tend to be found very close to their host stars, very different than the case of our solar system. So these are already multiple ways that our solar system is looking very unusual compared to the exoplanetary system.
So when you talk about super Earths, would that be a rocky planet that's larger than Earth, or would that be more of a gas type planet that's maybe smaller than the gas giants that we have in our solar system?
Right. So they have a range of gas components. So some of them are rocky. In fact, apparently some with very little atmosphere at all the way up to very thick atmospheres, and probably just water worlds, which are probably not habitable either. I think that you can make a good case that you need some land especially for complex life on a planet. For the carbonate silicate cycle to operate properly, the erosion off the continents provides certain important minerals like molybdenum, which is essential for all life, which molybdenum use an enzyme to fix nitrogen. The regulation of the salt content of the oceans happens on the continents. Whenever you have inland seas, you get evaporation and you get the salt deposited, and that's how you get these giant salt domes that are formed that are now mined in the continents. So salt has been gradually taken out of the oceans over Earth's history because of the continent. So there are a number of reasons to have dry land that are really important for life. So I don't think water worlds like these super Earths likely be habitable. Also, as well as you get more massive, you have higher surface gravity. And so there's less surface relief. So the difference between the lowest points and the highest points on the surface are smaller, because you can't build mountains as tall as we have on Earth because the base rock wouldn't be able to support the weight overlying weight from because of the higher surface gravity. And so you're less likely to have, even with the same amount of water that the Earth has, a super Earth would be less likely to have dry land because they would have less surface relief. So for those reasons, I don't think those very volatile rich planets would be habitable.
Very interesting. So just to follow up on the super Earths, if these are water worlds, Guillermo, does that encourage some astrobiologists, exobiologists that maybe there could be life if they think that there's liquid water there? Or are we talking about, for the reasons that you stated, there's still a lot more parameters other than just having liquid water? So, I mean, or do they still hope against hope that there could be life?
Yeah, from what I've read, the majority of astrobiologists recognize that a water world will be a problem. You really do need dry land for a number of processes for life. Yeah.
Okay, very interesting. Well, we're running out of time for this first podcast, Guillermo. I was wondering if you could stick around and we could do a second podcast on local and global fine-tuning.
Sure.
Okay, great. Well, I'm Casey Luskin with ID the Future. Stay tuned for more with Guillermo Gonzalez talking about his chapter in the book Science and Faith in Dialogue, titled Local Fine-Tuning and Habitable Zones. You can find it on our link that we'll put in the description of the podcast. It's a free open access book. Thanks for listening.
Visit us at idthefuture.com and intelligentdesign.org. This program is copyright Discovery Institute and recorded by its Center for Science and Culture.